So we've talked now about a uniform field. Let's talk about point charges. And remember that point charges do not create a uniform field. So if we place 2 point charges down, we know that each is going to have a repulsive force on it, assuming that these have the same signs. So for simplicity, let's just assume that Q1 and Q2 are both positive, but we're going to be able to generalize our answer to not have that not be the case. So let's assume that Q1 is staying fixed in position. That doesn't actually change the force that's acting on Q2. But we do know that as Q2 gets further and further away from Q1, that the force is actually changing. So that's pretty important. We're going to need to be able to deal with the force changing. So again, we're going to think about the work done due to the force of interaction, where the force of interaction is this Q1 exerting a force on Q2. We're going to have a distance, so from this we can again calculate that work. So charge 2 is what's moving, so that's why we're thinking about the force of 1 on 2. And now we must do an integral because the force is not constant. Before, when we just multiplied the force times the displacement with keeping in mind the angle in between them, we could do that because force was constant. Now because it isn't, we integrate. So what is the force? Well, this is just Coulomb's law. This one's simple. Q1, Q2 over the distance between. And right now, we are considering just a one-dimensional scenario, and we're going to call this direction x, but we can generalize that to be r at the end. So when we integrate this, note that 1 over 4 pi epsilon naught is a constant. That gets pulled out. Q1, Q2 is a constant. So really what we're integrating is 1 over x squared, and that's going to just integrate to be 1 over x, though I did lose a minus sign here. And you then evaluate it from x initial to x final. So because of the minus sign, this actually works out to be our x final on the bottom with the minus sign, and then a plus sign with our x initial. So I'm sorry about losing that sign here. But hopefully that integration makes sense to you, and we plug this in. We then are going to go through that procedure again of comparing potential energy or a change in potential energy based on work. So we then, again, flip the sign to get our change in potential energy. So we're flipping the sign again. And we then have x final minus x initial with all of these other terms. So from that, we can get the form for potential energy of 2-point charges. And it's just Q1, Q2 with that 1 over 4 pi epsilon naught out front, or this also gets called, remember, capital K. I prefer to not use K since we're also talking about kinetic energy right now. We have x on the bottom. Well, x was the specific coordinate that we integrated over, but you can imagine that any 2-point charges are always connected by a line. We could call that x, or simplicity, we're going to call that r. So r is just the spacing in between Q1 and Q2. So that's our potential energy between 2-point charges. So note that we need to think a little bit about zero potential energy. Again, for a ball in a gravitational field, we usually consider the surface under it, the ground, to have zero potential energy. But that really actually varies whether you're standing on the 3rd floor of the building or whether you're on the ground. So we really can choose zero potential energy to be wherever we want. And here, it does not make sense to say r equals 0 is where potential energy equals 0. Notice that if I plug r equals infinity in, I am naturally going to get 0, right? I say, of course, r equals infinity. If you're a mathy person, you're going to want the limit as r goes to infinity. But yeah, so don't be too much of a physicist if you don't want to be, but we can say r is going to infinity, and we then see that u goes to 0. So what that means is that if our 2-point charges are infinitely far apart, really, again, not just very far, but infinitely far apart, well, at that point, they're not interacting. So there's no potential energy. So one thing that's important to note as we set the potential at infinity to be 0 is that if I bring 2 oppositely charged particles together, that should be decreasing the potential energy, right? If Q1 and Q2 are both positive, this whole thing is positive. If Q1 and Q2 are both negative, I again have a positive value when I multiply them. But if one is positive and one is negative, potential energy is then negative entirely. And additionally, if you think about this, that two oppositely charged particles at infinity are actually going to accelerate towards each other if you bring them slightly in such that they are allowed to interact. So that means that their potential energy must be decreasing if their kinetic energy is increasing as they speed up as they get closer. So we actually set potential energy to be 0 at infinity for point charges all of the time. But if they're oppositely charged, one's positive, one's negative, potential energy decreases, which means it must be negative. And we'll actually look at some plotting of this that might help with this idea, but I find that many students mess that up. So what if we have more than 2 point charges? I think the book presents this in a slightly confusing way, and there's really two things to think about. First, we only need to consider potential energy for pairs of charges whose spacing is changing. So in this example that the book does, there's a before scenario and an after scenario. Now we have 3 point charges, but charge 1 and charge 3 stay fixed. Charge 2 is the only one that moves. So we need to worry about this spacing and this spacing, but we don't actually need to worry about the spacing between 1 and 3 because 1 and 3 remains the same. So there is potential energy here, but it's not changing, so you don't have to worry about that at all in your problem. So in this case, we would actually have 2 terms to worry about, the potential energy between these two and the potential energy between those two, and it's changing as this one moves. So the book writes it this way, that our potential energy is then going to be a sum, this means that we're summing, over Qi, Qj, over Ri, J. And that just means use the distance between these two charges. The reason we're doing a sum is that you need to consider each pair. Why does it say I less than J? Well, we just want to do that only once. So you don't want to consider, for instance, the potential energy of 1, 2, and then 2, 1. Don't do that. So this is, I think, if you're not used to this sort of index notation, a confusing way to write it, but really what we're trying to do is sum the potential energy right here from each pair. So think about it that way, and just you can simplify the problem by ignoring any pairs that don't change their spacing. So that's how you can approach this, and you're going to have more practice with this, and it's probably going to make more sense as we learn about potential and some additional concepts in this chapter.